Good morning, everybody. Hope you are all healthy and safe. So, we are going to continue with our lecture on linear equations. So, in the previous lecture, we had seen what is meant by a linear equation, and we had also discussed how to solve it. That is, by writing it in a standard form and finding the integrating factor, we can find the solution of the linear differential equation. Now, in this lecture we shall be discussing about the concept of a piecewise differential equation. That is, the differential equation is given as a piecewise defined function. Okay, this happens mainly in case of most of the mathematical models which we are dealing with in our day-to-day life, especially in biological sciences and engineering, that one or more coefficients in a differential equation is a piecewise defined function. That is, either p of x or f of x is a piecewise defined function. Okay, that is, it is not we shall look into the example to make much more clearer. That is, in a particular portion of the interval, a function is defined as like you can say f of x is equal to 0 for values from a to b, and it is equal to x plus 1 from values from c to d, or from b to d excluding b. So I hope you get the idea. So just keep in mind, it's like a discontinuity in the function of either p of x or f of x, which is in the standard form of a differential equation. So this happens mostly in case of mathematical models. So since we are considering about the practical application of everything, we have to learn about this type of differential equation also. Okay, so let's see the example which is given in your textbook. So it's example 5. It is an example of an initial value problem in which the corresponding f of x, okay, that is piecewise. So you can see, solve, the question is solve dy by dx plus y is equal to f of x, and the initial value is y of 0 is equal to 0, where f of x is piecewise defined, that is equal to 1 in the interval 0 to 1, and whenever it is greater than 1 it is 0. So you can see the figure of f of x. It is a discontinuous function. You can see from 0 to 1 it is the line y is equal to f of x equal to 1, and all other where it is equal to 0. Okay, so how do we solve this? We solve this by two methods. Not two methods, we solve this separately. First we'll consider differential equation dy by dx plus y is equal to 1 and solve the differential equation. So that will give the value in the interval, or that will give the solution in the interval 0 to 1, and for all values greater than 1 we will get the differential equation will be dy by dx plus y is equal to 0. That will be a homogeneous differential equation. Okay, so how do we solve it? The first case is dy by dx plus y is equal to 1 for 0 less than or equal to x less than or equal to 1. So in this case, this is our already in the standard form. So here p of x is equal to 1. So integral will be, or the integrating factor will be e raised to integral of 1 into dx, that is e raised to x. So the solution will be y into e raised to x, which will be equal to integral of e raised to x, which is e raised to x itself, plus the constant c. So when we divide it by e raised to x, we get y is equal to 1 plus c1. Here they have taken c1 as a constant, integrating constant. 1 plus c1 into e raised to minus x. Okay, so now if you look at the function f of x, 0 x is equal to 0 when f of x in the position where f of x takes a value 1. So in this case we'll have to consider the initial value. Here we don't have 0, x is not 0 here, so we don't have to consider this initial value. Okay, so we'll have to determine the integrating constant in a different way. So here we have y is equal to 1 plus c1 into e raised to minus x. This was a solution which we have obtained by solving the standard form of linear differential equation. Now since y of 0 is 0, what do we get? 0 is equal to 1 plus c1 into e raised to 0 is 1. So 1 plus c1. So from this we get c1 is equal to minus 1. Therefore, the solution in the interval 0 less than or equal to x less than or equal to 1 is y is equal to 1 minus e raised to minus x. Okay, I hope it is clear. Now next, the interval is from 1 to infinity. Okay, so in that case our differential equation will be dy by dx plus y is equal to 0. So here again same solution, except we don't have this is a homogeneous differential equation, so the solution is same as before. We get y is equal to, or y into e raised to x is equal to integral of 0 or equal to the constant c2. So y is equal to c2 into e raised to minus x is the solution. So we can write the solution in the following manner, that is y is equal to 1 minus e raised to minus x when x lies between 0 and 1, including 0 and 1, and it is equal to c2 into e raised to minus x whenever x is greater than 1. Okay, so now to find c2, what do we consider is, we consider that the solution must be continuous, right? So at particular, the discontinuity is happening at the point x is equal to 1. There is a discontinuity, so at this particular point we'll have to consider the function should be continuous. So for the function to be continuous at 1, the left hand limit and the right hand limit must be same, that is both these values at x is equal to 1 must be same, equal to y of 1 also. Okay, so these must be equal. The requirement that limit x tends to 1 plus y of x is equal to y of 1. So when it is equal to y of 1, we will get c2 into e raised to minus 1 is equal to 1 minus e raised to minus 1. Solving this, we get the value of c2, which is equal to e minus 1. So just substituting it, we will get the required solution. So this is how we solve a piecewise differential equation. So either the p of x, the function p of x, or the function f of x, which is in the standard form, will be piecewise, that is, it will be discontinuous. So we just have to consider the separate intervals and solve it as a normal differential equation, and just combine it and write the solution. And just take care that if it is an initial, in this case it was an initial value problem, just take care that the initial value, in which interval does the initial value lie, corresponding to that interval we will be able to determine the constant. Otherwise we have to consider the continuity of the solution and find the integrating constant. So once we do more examples, the concept will be a little bit more clearer. Now that was about piecewise differential equation, which is coming into picture due to the practical application of differential equation in most of the mathematical models. So next we shall move on to the end of this section, that is we are going to discuss about a function called as the error function. So in calculating everything practically, if you are looking into practical applications, there can be a slight error, small, very minute errors can happen in all types of calculations because of many variations, because the factors affecting the things that we are considering, there are many factors. So error function is something which we calculate during solving the values or finding the solution. So here there are two types. We are going to discuss about two types of functions. One is error function and the other is complementary error function. Okay, there is a very slight difference between them. The error function is denoted by ERF of x, okay, and the complementary error function is ERFC, C for complementary. So error function of f of x and complementary error function of f of x. So this is given by nothing but 2 by root pi integral 0 to x e raised to minus t square into dt, and complementary error function is from x to infinity. Okay, the same value, but the integral, the limit varies from x to infinity. Okay, so just keep these two formulas in mind. One is of error function and the other is of the complementary error function. Now there is a note which is given in this slide, that is error function plus complementary error function is always equal to 1. Okay, this is due to the result that integral 0 to infinity e raised to minus t square into dt is nothing but it is equal to root of pi by 2. Okay, this is equal to root of pi by 2. This is the well-known result, that is the integral from 0 to infinity e raised to minus t square dt is equal to root pi by 2. So what will be if I take this to the left hand side? So I'll get 2 by root pi integral 0 to infinity e raised to minus t square dt is nothing but equal to 1. Okay, now the sum of these two functions are nothing but 2 by root pi integral 0 to infinity e raised to minus t square dt equal to 1. So I hope that concept is noticed. This is a simple proof. It is because of this result. Okay, so just keep these functions in your mind and just remember this formula. So suppose there can be questions asking to determine the error function, so just keep in mind these formulas, just go through it. Now there is another last example which is given in your textbook, which depicts the concept of this error function. So it is as follows. So you can see that they are asked, it's just a normal differential equation initial value problem which is given to us. So we have dy by dx minus 2xy is equal to 2, y of 0 equal to 1. So this differential equation is linear, it is in the standard form. So here what is p of x is nothing but minus 2x. Okay, and f of x or q of x is equal to 2. So the integrating factor will be e raised to integral of minus 2x dx. Okay, that is solving, we get it is equal to e raised to minus x square. So the solution will be y into e raised to minus x square, which will be equal to integral of 2 into e raised to minus x square into the corresponding dx, what will be it. So here you can see one thing, that is the right hand side will be 2 into integral of e raised to minus x square dx. Okay, so e raised to minus x square dx, it does not have a standard integral value, but we cannot find it easily. So what we consider is we consider it as 2 into integral 0 to x e raised to minus t square dt. Okay, so we get it is e raised to minus x square into y of x minus here we'll have to apply our initial value, that is y of 0, that is the integrating constant, right? So minus y of 0 will be equal to 2 into integral 0 to x e raised to minus t square into dt. Now what is y of 0? Y of 0 is 1, it is given to us. So we can substitute it and we'll get the solution to be y is equal to e raised to x square, taking y of 0 equal to 1 on the other side and dividing throughout by e raised to x square. Okay, so we get e raised to x square plus 2 into e raised to x square integral 0 to x e raised to minus t square dt. This is the solution of the differential equation. So here just keep in mind this is a special case when the integral is a non-elementary integral, that is integral e raised to minus x square, e raised to integral of e raised to minus x square, that is not it is not a standard value, cannot be determined. So we consider it to be the value from integral 0 to x e raised to minus t square dt. Okay, and then we apply the initial value and the solution is given to be y is equal to e raised to x square plus 2 into e raised to x square integral 0 to x e raised to minus t square into dt. Now just to show the the error function, what we do is we are multiplying and dividing by root of pi, where in this expression. Okay, only in this term we will multiply and divide by root pi. So what do we get? We get this is I'm taking a raised to x square common, and this is a raised to x square into 1 plus root pi into 2 by root pi. E raised to x is taken out common. Okay, so 2 by root pi into integral 0 to x e raised to minus t square dt. So integral 0 to x e raised to minus t square dt into 2 by root pi is nothing but our error function. Okay, so sometimes the solutions can be written in terms of error function also. That is, the solution can be written as y is equal to e raised to x square into 1 plus root pi error function of x. So it can be used to determine the solution, the error function that we have learned just now. So this is how we solve the linear differential equations and apply the error function to just find the solution in terms of error function if we are asked to find it. So just keep these formulas in mind, and we shall be discussing more problems and we shall be doing more exercise problems, working it out so that we can get the concept more clear. So that's it for today's session. Thank you. Stay safe and stay healthy.